ROS developers, and welcome to a new live class number 128. So today we are going to be working a little bit with the ARI robot from our colleagues in PAL Robotics, which is a super interesting robot which has many features. It's especially designed for human interaction, and we are going to be reviewing some of these very cool features today in this live class. So yeah, let's go for it. Let's not lose any more time. Then let me very quickly share here my screen. There we go. So as always, I'm going to show the process in order to get to the live class. So here in workshops, remember that here you're probably now seeing the live class. Here I am seeing right now a live. So what you need to do here, very important, is to click on this fork and open the class rosject. Okay, so by clicking here, you are going to get a copy to your account of the rosject that we are going to be working with in today's live class, and it's going to also automatically open this rosject. So let me click the button myself, and this is going to redirect me to the rosject page, where you are going to be also able to see the live stream, to see what I am doing, also to listen to me, of course, but at the same time, in the same environment, you are going to be able to work and to test all the different demos that we are going to be doing. So yeah, here myself, my environment is getting loaded, as you can see. It might take a little bit because it's a quite huge project. Also, I can start seeing here your comments. Ali Khalifa, Anitha Joel, hello there. Welcome everybody. Say hello if you are here around. Say something in the chat so that I can know that everything is okay. So is the live streaming okay? Sound is okay? Are you loading your rosjects like I am doing? Yes, no, let me know. Of course, if during the live class you have any question or anything, just let me know here in the chat, and I will be here checking it in case you have some questions or anything. Yeah. Okay, so no comments so far. So I will deduct that everything is okay. All right, then let's just wait here until my rosject loads. Meanwhile, let me share here, let me explain a little bit about it. So basically today we are going to be working, as I have said, with the Tiago, sorry, not the Tiago, with the ARI robot. Then we are going to be covering some things, some demos related to especially three very important ROS fields, which are navigation, manipulation, and perception. Okay, so we are going to be covering a little bit of everything. Then I want to remind you that, of course, in our academy you can find courses. You have them here linked. Also in the notebook inside the rosject, I will show it to you in each demo, which course would be available, because, of course, since the time for live classes is limited, we are not going to be able to go too much in depth into what is going on. So we are going to basically show the demo, show the functionality, but we are not going to be able to go that much into what is really going on behind the scenes. So all of this you can get it, of course, in our courses in the academy. Especially for this one, we are going to be applying, as I have said, the three of the most important fields in robotics and in ROS, which are perception, manipulation, and navigation. Okay. Also, let me remind you that we have also another course about another robot from PAL Robotics, which is Tiago. Also a super cool robot, so you can check all these courses here in the academy. Let me come back here. All right, so my rosject has already loaded. Then once your rosject loads, you should see something like this. You should have the rosject for today's live class, ROS Developers Live Class number 128. Okay? So please let me know if everything went okay here. So were you able to copy the rosject and open it? Yes, no. Please let me know so that I can know. Yes, okay, says Joel. Great. Okay, so yeah, as you can see, also Ali, yes, Vedant, perfect. Okay, so we are good and ready to go. Then today's live class is going to be in collaboration with our colleagues of PAL Robotics, which is a company also based here in Barcelona, but is well known worldwide, especially for their humanoid robots. So today we are going to be checking one of them, which is the ARI robot, right? And we are going to be checking some very interesting features related to this robot in this project, always basing everything in simulation. So we are going to be launching a simulation and testing different features related to the ARI robot. All right. Then, yeah, let's not lose any more time and let's start. So we are going to start the first simulation. So for that, we are going to open a new shell, all right, which is here the first icon that we have here in the bottom bar at the left, which says web shell. All right. Then here we are going to first of all source the ARI public workspace. So if we run here an ls command, we are going to see that we have different workspace here in our rosject. In this case, we are going to be sourcing the ARI public workspace, which is the workspace where we have all the packages and everything related to the ARI simulation. Right? Then we can have a look also in using a graphical interface, which is the IDE here, or code editor. So if we click here, I'm going to open it right now also because I'm going to be coming back here to the IDE through the live class. So here basically you can see the same. So all these workspaces, etc. And among them we have here the ARI public workspace, which is the one we are going to be working with today, right? Then here inside this workspace, in the SRC folder, we are going to see all the packages related to the simulation, which are a lot, as you can see. Yeah, so this is why this project is quite big. So here we have all the packages which are related to the ARI simulation. Then we are going to be checking some of them. But for now, let's just launch our first simulation, which is done with this command. ROS launch ARI gazebo.launch, and we specify this public sim argument to true. So let me directly copy and paste these two commands. So first, the source. Let me copy and paste it directly here to the web shell, and now I'm going to run this second command, this ROS launch command. There we go. So this is going to start loading everything. We can have a quick look at this file and see basically what we are doing here. So this package, this ARI gazebo package, you can find it in ARI simulation, okay? It's easy to detect in any case. We can do here a source public ARI public devel setup bash. We source the workspace, and then we can run a roscd command, for instance, in this case to the ARI gazebo package, and this is going to show us where this package is. In this case, as you can see, it's inside ARI simulation. So here inside ARI simulation, we can find the ARI gazebo package, and inside the launch folder, we are going to find different launch files. In this case, the one we are running is ARI gazebo.launch, right? So we can double click on this file, and this is going to open this specific launch file. All right, and here we can see basically the file that we are running. So what is going on here? As you can see, we have many arguments being loaded, some other launch files which are included. So here, for instance, we are starting up the world environment, which in this case is empty, is an empty world in this specific case. Here in this RE spawn.launch, we are spawning the robot into the world, into the gazebo world, and finally we are bringing up the robot, we are bringing up all the controllers, etc. So we are bringing the robot to life, let's say. All right? Okay, then here where I have my command running, now I have the simulation running. So in order to visualize it, what I have to do here is to click on this cube-like icon, as it is indicated also in the notebook. So if we click here, this is going to open the gazebo client, basically, and it's going to allow us to visualize the simulation, as you can see here. Yeah, so here we have the RE robot loaded, in this case, in an empty world. Okay, in the other demos, we are going to be launching different worlds. In this case, we are just launching an empty world with the RE robot spawned in it. All right? Then, yeah, so here we have already the simulation. In this case, the simulation is going to be a little bit slow. As you can see, real-time factor is 0.34. So for this live class, we are using instances, we are using computers, which are not very powerful, let's say. So everything is going to be slow, but it should work properly. All right? Then, yeah, so let's keep going. So we have our simulation running, and we have launched other things, as you can see here, like the move group from Move It, which is very directly related to the demo that we are going to run right now, which is to execute predefined motions. So the RE robot provides an action server, a ROS action server, which is called Play Motion. And this action server allows us to execute some motions that are already predefined. For instance, a wave motion and others. Okay, we are going to see the available motions. So basically all these motions are defined here in a YAML file, remotions.yaml. Then this YAML file, the data inside this YAML file is loaded into the ROS parameter server. So let's have a look at this launch at this YAML file first, which is in RE bringup. So let me look for this RE bringup package. RE bringup. Okay, so we have it here in RE robot. So let's look for it. It's inside RE robot. RE robot. Here it is. RE bringup config motions and remotions.yaml. Yeah? So here we have it. remotions.yaml. Then here, as you can see, we have all the motions defined. Start RE, bow, wave, look around, etc., etc., etc. So all the motions are defined inside this YAML file. Then all this data is loaded into the ROS parameter server so that we can access it, so that ROS can access at any time all this information. Then we can run another command here, which is indicated here in the notebook, this one, which is going to allow us to see all the different motions available. So let me copy and paste this command here very quickly, which basically I'm running a ROS param list and then I'm filtering the results. So here I can have a list with all the motions available: bow, look around, nod, shake left, shake right, show left, show right, start RE, and wave. All these are the motions available. All these also we can get this information also from this file, of course. In fact, here we have all the information related to the motions, like the joints which are involved in each motion, which are all the positions of the different joints in order to achieve this motion, etc. Then we can also access all this data from the ROS parameter server. For instance, we can get the information of the joints which are associated to one specific motion, or the points that the joints have to achieve, have to reach in their trajectory in order to achieve this specific motion. Then we can get also information about this by just calling using the ROS param get command in order to get information from the ROS parameter server. In this case, for instance, we can get information of the joints which are involved in the wave motion by running this command here. So let's do it ourselves. Let me run this command here. And here I am getting the information of the joints which are involved in this wave motion. And as well, I can get information of the points that these joints have to achieve in order to complete this wave motion. This is done by accessing the parameter play motion, motions, wave, points. So we can also run this command here in the shell, and this is going to return the information of the positions of each joint. All right? Hello Marco, also Maria, Ruben, hello everybody, all the newcomers. All right, so yeah, all of this is super nice and super cool, but let's try it, right? So what we want to really do is to try it and see the ARI robot in action. So for this, basically what we have to do is to send a goal to the play motion action server. So the play motion, as I have said earlier, is an action server provided by the ARI robot. Then in order to call this action server, we need to send a goal to it, right? Then we can send this goal to the action server in many ways. We could send it directly by publishing into the goal topic, for instance. We can create an action client and a script in C++, in Python, which sends a goal to this action server. But in this case, for this live class, we are going to use the AX client tool, which is a very convenient tool that allows to send goals to ROS action servers in a graphical way, in a very simple, user-friendly and graphical way. Did you know AX client? Have you used it before? Well, if not, we are going to have a look at it today, and you are going to see that it's super simple to use. So in order to run it, to execute it, we are going to source again the ARI public workspace. So let me source it one more time. And now I'm going to run this command, ROS run actionlib axclient.py play motion. So let me run this command here. So as you can see, basically here what we are doing is to run this AX client py, which is going to start up the AX client graphical interface. And then we have to specify the name of the action server we want to connect to, which in this case, it's play motion. Then this is going to start up a graphical application, which we can see by opening the graphical tools. So if we click here in the graphical tools icon, which is this computer-like icon here, this is going to open the graphical tools window, and this is going to allow us to access basically graphical applications, like in this case this AX client, RQT applications, RVs, etc. Then here we have the AX client application, which is very small. You can double click here in order to maximize it, so that you can see it better. Then, as you can see, this is it's very simple. It has three different windows, panels. The first one is for the goal, the second one is for the feedback, and the third one is for the result. So in the goal section, we have three variables, which is the motion name, skip planning, which is set to false by default, and priority, which is also set to 0 by default. Then all we have to do here, in order to send a goal to the motion play action server, is to fill in the information here related to the motion name. So here, between the brackets, we are going to need to write the motion that we want to execute. For instance, wave. So we know the name of the motions because we have checked them before. Here we can check them in fact again. Let me copy this command and run it one more time here so that I have the information available. So let me open yet another shell. Source again, super important. We have to source the ARI workspace so that we have access to all the packages, messages, etc. related to the ARI simulation. There we go. Then here we have the name of all the motions available. So you can really choose any of these. I'm going to run, in this case, for instance, the wave motion. So you select the name of the motion you want to run, and you have to fill this name in the motion name variable here of the goal section. Then once you have completed this information, all you have to do is to click here in the Send Goal button, down here. All right? Of course, all these steps that I am doing now by myself, all of this, it is explained in the notebook. Okay, so you have everything explained here. Then if you get lost at some point, of course, you can ask in the chat, or you can come back here to the notebook and check all the steps. All right? Then, yeah, so once we have the motion that we want to run, then we click on the Send Goal button. And the goal is going to be sent to the Play Motion Action server. So let me click here in the goal. Okay, so now if I come here to the simulation, we should see the ARI robot perform the wave motion. As you can see, it's starting to run the motion. Let me make this bigger. There it goes. It has a little bit of delay, of course. It's going slow because of the resources that this simulation takes. But we can see here the wave motion, how it's being performed. See? It's moving the hand. And there it goes. It has finished it. Okay, great. So we have done the wave motion. Then we can run another one. Let's test a different motion now. For instance, we can test the look around. For instance, let's try this one. Let me come here then and run the look around motion. So let's send the goal. And now, as you can see, the ARI robot is moving his head to the sides, so it's looking around, basically. Okay, so yeah, as you can see, this AX client tool is super convenient, especially for people who doesn't have much experience in robotics, in ROS, or in computers in general, because it allows to interact with a ROS action server, which is a quite complex topic. It allows to interact with these action servers in a very easy and intuitive way, right? So yeah, as you can see also, here we are getting the result, the error code in this case, which is 1, and we can see also here the status, the final status of the goal, which in this case it has been succeeded, right? In case that there is something wrong, of course it's going to show here failed or whatever. But in this case, everything is working as expected. All right? So yeah, so far so good. Have you been able to run yourself the motions in the robot? Yes? No? You have to bear in mind this, that it's going to go slow, because of course these computers that we are running this rosject on, they don't have that much resources, and this simulation takes a lot of resources. So yeah, but you are going to see this motion in slow-mo, let's say. Yes, it works, Joel. Okay, great. Then Yeah, so let's keep moving on. So, well, yeah, of course, all of these motions, well, let me get a drink. 1 second. There we go. So all these motions, of course, are being executed. So yeah, let's come back very quickly here. So here we have all the information related to the motions. Let's grab one here. For instance, the look around. The look around motion has information of the joints involved. So in this case are two, the head 1 joint and the head 2 joint. And then in points here we have the time from start, 0 seconds, 2 seconds, 6 seconds, 8 seconds, etc. And the positions of each of the joints in order to complete this specific motion. Yeah, for the wave is a little bit more complex, as you can see here, because it involves more joints, which are the hand joints. Okay, so here we have also the time from start and the positions of each of the joints in order to achieve this complete motion, wave motion. Then all this is happening also thanks to Move It, which is running here in the background. As you can see, we have here the Move Group node launched, which allows all these motions. Then in case you want to learn more about this, here we have also a GIF of the expected result. Then yeah, so in case you want to learn more about trajectory execution, motion planning, Move It, etc., I have left here a link to the ROS manipulation in 5 days course, which you can click here in the image and it's going to take you to the course, where you are going to be able to learn much more about what's going on here in the background of this super nice demo. Okay, so in case you want to learn more, you are going to find all this in the ROS manipulation in 5 days course. Okay, then let's keep going. So, of course, for a humanoid robot which is going to be interacting with humans, of course, a super important feature is to have perception. So, ARI robot provides perception in many ways. It has, for instance, corner detection. It can also detect objects and estimate the position of these objects. It also provides corner detection. It can also detect Aruco markers, etc., etc. In this case, we are going to run a demo on people detection, person detection, okay? Which is, of course, also something super interesting for this kind of robots, because since they are expected to be in environments with humans, it's very interesting that the robot is capable of detecting a person. And also, by the way, we are not going to do the demo, but it also provides face detection, okay? So it can detect the face of a specific person. So this is super interesting because it allows the robot, for instance, to detect a person and go near that person. For instance, run the wave motion in order to say hello to this person, and it allows many interesting and cool interactions with humans, right? So yeah, in this case, the demo we are going to run is going to be using OpenCV, okay? In this case, it's using an ADA boost algorithm, etc. All these technical details, I'm not going to go through them, but in case you want to learn more related to this, also I have shared here the OpenCV Basics for Robotics course, which we have in our academy and which overviews lots of these concepts here. For instance, here we have people-related OpenCV functions for detecting people, detecting faces, etc., etc. So in case you want to learn more of the background associated to this specific demo, also I have left you here this OpenCV course, okay, so that you can check it in case you are interested. Then let's go with this demo. But of course, if we want to detect people, the first thing we need to have is people. And in this case, we don't have people in this simulation, right? So yes, we are going to need to change the simulation. So let me come here and stop this simulation with Control C. There we go. So we have stopped the simulation, and then we are going to be starting a new one. You have indicated here. So let's run this new simulation. As you can see, we are running the same command. So it's ROS launch ARI gazebo.launch, which is the same command that we have launched for this one. But in this case, we are changing the world. We are specifying a different world. Okay? If you don't specify any world, then it's going to load just the empty world. But if you specify a specific world, then it's going to load this world. Okay? The available worlds also, you have them here in the ARI gazebo package. It's here. Where do I have it? Here, PAL gazebo worlds. Here you have many worlds available, okay? As you can see, in this case, we are going to be running the tutorial office world, as you can see here, tutorial office world. So we are going to specify this world here as an argument, and then we are going to run this new command, which is going to, oops, sorry, I didn't copy the command properly. Let me just copy it again. Paste it here. Okay, there we go. So now we are going to load again the ARI robot, in this case, in this tutorial office world, which is going to look something like this. It has two different rooms, and basically the important thing about this simulation is that it has people in it, as you can see. We have 1, 2, 3, 4, 5 different persons here in this office environment, which is going to allow us to test these people detection algorithms. So let me go back here to the GC client, and yeah, so here we have the simulation. Let me get a bit closer to it. With all the people, etc. Then, yeah, this is also going a little bit slow. There we go. But, well, you can see all the different persons here, which are distributed around the different rooms. Then, yeah, so let's try it. We can already stop the AX client, by the way. We are not going to use it anymore. You can use it later if you want to test other motions. So now for this people detection, we are going to be using this PAL person detector OpenCV package, which is a package created, as you can see, by the guys of PAL Robotics. It's in their repository. It has been created by them, and it's maintained by them, and it's going to allow us to execute this people detection. You can have a look at the code more specifically here. Also, of course, the same package, you can find it here in the IDE. We have, of course, downloaded here. Here we have it, PAL person detector OpenCV. All right. So yeah, we are going to run this node here with the following command, okay? We are going to run the detector.launch file, which you can find here, detector.launch, okay? So you can see, basically what this is doing is to run from the PAL person detector OpenCV package, is running this PAL person detector OpenCV script, which basically is the script that we have here. And we are setting here some topics, etc. So let's run this command here. Let me run it right here. We are specifying here the image parameter, which basically contains the topic name of the image that the camera, which is mounted in the ARI robot, contains. So let's in order to better understand a little bit, to understand better this, we are going to run another graphical application, which is RQT image view. So this application is going to allow us, as you can see, to get in real time the images that the camera of the head of the ARI robot is getting. So let me run in a new shell. Here, in this case, I'm going to run it here in the third shell. I'm going to run this command in order to start this RQT image view application. There we go. And again, this application, we are going to be able to visualize it in the graphical tools. Okay? It might take some seconds to get started. Just be patient. There we have it. Okay. Then we can maximize it, of course, to get a better view. Now here, as you can see, we can select between all the different topics that the cameras of the robot provides. As you can see, it has different cameras. It has one camera in the head, at the front of the head. It has another camera in the back of the torso, another camera in the front of the torso. Then in this case, the one we are interested in is the camera in the head. It's the one that we are going to be using to perform person detection. So if we select the first topic in the list, which is this head front camera / color / image raw, we are going to get the images that the robot is getting in real time. So this is what the ARI robot is seeing right now, which, as you can see, the robot, we have it here, and then this camera is indicating this person that it has here right in front, right? This person that is here, standing here in front of the robot, is the one that we are detecting right now here in the camera. Then the person detector, the person detection script algorithm, what does is it processes this image, and then once it detects that there is a person here, it's going to write a bounding box around this person. Yeah? Which is known also as a ROI, a region of interest. Is going to publish here a bounding box where the algorithm, where the program thinks that there is a person. Then it's going to publish this information into a specific topic. In this case, it publishes this information into this person detector / debug topic. Okay, once it processes the image and it detects, in this case, a person or not, it's going to publish this information into this topic. So we can also select this topic here in the list, as you are going to see, person detector debug. Then if we select this topic now, we are going to see the same image in real time, but we should see a bounding box, as you can see here, around where the robot thinks that there is a person, which in this case it's quite accurate, right? So we can try, for instance, we can try to trick the robot here. So for instance, if we move here, I'm going to move manually here the person a little bit, directly using the GC client. I'm going to move it a little bit, and let's see if the algorithm reacts properly or not. Of course, this might be extra tricky in this case because the simulation and everything has a little bit of delay. But I want to put it a little bit into test. So let me try this. Let me move the robot here a little bit to a side. I'm doing it right now, slowly. There it goes. I have moved it. Okay, so let's see when it gets updated in the camera and everything. And if the region of interest gets properly updated. Maybe let's try to refresh here the topic information. And let's see if it gets properly updated. I'm not sure if it has moved or not yet. Let's see if I change. Okay. I'm not sure if it has moved or not because I don't remember the previous position. But yeah, in any case, the end result, let me move it more actually, so that it's more detectable. Let me move it closer here to the table, which is being detected here. Okay, let me see if I can. Okay, so how about you? Have you been able to do the person detection? Have you been able to run it and it's detecting here the person which is right in front of the robot? Yep, no. Yes, says Ali Khalifa. Okay, great. By the way, another thing that we can do instead of moving here, which is not a very good practice, person detection worked. Great. Instead of moving the robot here manually, which is not a very good practice, what we can do, and in fact what it is recommended in the notebook, is to actually move the robot, which is much more convenient, right? So we can do this very easily also by running this key tailor program. So let me try it. I'm going to try it here. So let me open right here a new shell. Source the ROS workspace and then run this command here. ROS run kteleop.py. Okay, so this is going to start this program, which as you can see, it allows to move the ROS robot by using the arrow keys in your keyboard. Okay, so I'm going to do it here myself. Then you have to put the focus in this shell here. Let me move this a little bit to a side. Okay. Okay, so now as you can see the robot is moving with a little bit of delay, but basically I am hitting on the arrow. On the up arrow, so the robot is moving forward, as you can see. Okay, I'm going to move it a bit more forward. It's going with a little bit of delay, but we can see here in the simulation how the robot is moving forward. Okay, you can turn it, etc. You can basically control it with the arrow keys of your keyboard. Okay, so let's go back here, and as you can see now the person is much closer. See, so we are getting the image here updated. We are now much closer to the person, so let's see if the robot can detect also the person if we get closer to it. So let me see here in the person detector debug topic, and as you can see now it's also being able to detect the person, right? So now what you can do basically is to start moving the robot all around the room in order to try to detect the different people in the different rooms. And you can check and verify if it currently detects all the people that are, because we don't only have this person here in this simulation, but we have different persons with different shapes, etc. So you can test if the robot is able to detect all of them properly, which is quite interesting. So you can turn it around, for instance, in order to face this other person, which is there in the other corner of the room. As you can see, I am now rotating the robot. I am turning the robot so that it faces this other person. keep rotating here. For me, he detects the picture of ARI on the wall. What do you mean? It doesn't detect people? Or... See, so now I am facing this lamp. Unfortunately, it's not detecting it as a person, which it could. If the algorithm was not too good, maybe it could detect this as a person, which it's not being the case. Okay, so here we are still rotating here. Here I can see the poster, which also, by the way, it has other algorithms in order to detect here the features of this poster, etc. So it can also do that, but we are not going to cover this on this live class. So yeah, let me just finish here rotating the robot a little bit more so that I can put it there in the direction of the other person. There it goes. I think with a couple more, and it's going to see this person in the corner. There it goes. Yeah, here we have it. Okay, so now I have it faced to this other person, and now I'm pretty far away from this person, actually. But even though it's being able to detect it. Okay, so it seems that this algorithm is working pretty well, right? So here I am detecting also this other person in the corner. So yeah, I'm going to leave it. Here you have also another panel where you can do different detection, demonstrations and tests, etc. All right, so I'm going to stop this demo here and go for the last one. So let me stop everything here. Okay, so again, let me remind you, if you are interested in learning a bit more about these specific features of OpenCV, how OpenCV works, Aruco detections, people detection, face detection, etc., you can learn about all of this in the OpenCV Basics for Robotics course. All right? You have by clicking here on the image, you are going to be taken to the course. Also the ROS perception course, by the way, which is another course that we have also in the academy, also is related to this ROS perception course. All right, so in this case, we are going to go straight to the last demonstration, which is the navigation demo. Then for this last demo, we are going to need to install some things. So we are going to, first of all, come here to the ARI public workspace. Then we are going to run this rosdep update command here. And we are going to run also this command here, rosdep install. We are going to install some dependencies, which they are not installed by default right now in the rosject, but in the following days after this live class, we are going to install them. So this step is not going to be any longer required, okay? So far, in order to make sure that all the dependencies are installed, we are running it. Sorry, you need to run before this a sudo apt-get update, okay? So before this rosdep install, we need to run a sudo apt-get update. Here, sudo apt-get update. Okay, then as soon as you run this command, it's going to start installing some things, as you can see, some packages. And as I have said, we are going to install this by default in all the computers after this live class. So you are not going to need to worry about this if you work later on this project, okay? We are just doing this for this live class because we didn't have time to automatically install these packages in the default computers. So that's why we are doing it here. But yeah, they are going to be installed after this live class in the default computers, so that you don't need to do this, okay? Our Jupyter notebook has no setup section before autonomous navigation. Okay. Nobody has this setup section? Does nobody have it? Yes? Ahmed has it? Okay. That's strange. I have not. Okay, you don't have it. Okay, then maybe this didn't get saved in the last version, because this is one of the things that I added the last. So probably this didn't get saved. Okay, don't worry. Then, in any case, after the live class, you are going to be able to do a pull in order to get the latest changes of the rosject, so that you are going. In any case, this section, the setup section, after this live class, as I have said, is not going to be required. So in any case, it's not that important. So let me copy this here. I'm going to copy these commands here in the chat so that you can run them as well. Okay. So I copy them here in the chat so that you can also copy and paste them here directly. Okay, the last one did not copy properly. Oh, maybe I have. Yeah, there are. This command is too big to paste it here. Okay, well, in any case, just by running this one, sudo just by installing this one, you should be fine to go. Let me try to find it. Okay. Yeah. ROS spatial temporal voxel layer. Spatial temporal voxel. Okay. Yeah. So just by installing this one, you should be good to go. Okay. So forget about all these ROS Dev install. Just forget about this command here, and just go for this one. All right. Then you're going to need to run also this command in order to do some preliminary setups that have not been done by default. So I'm going to run it also here. Let me paste this command also here. Okay, there we go. Then now we are ready to go. Okay. So now we are going to source again. In this case, I don't need to do it here because I have already sourced it previously, but we can source just again to make sure that everything is okay. And then we are going to run this command here. Okay, we are going to launch a different world in this case, which is this one, and we are going to be running this ARI navigation launch file. So let me copy this command here and run it. So this is going to start this new world, as you can see, this different world, which should be loaded here. And then here we are going to automatically start move base. Okay, yeah, so here I have the world loaded. There we go. All right. And here in the IDE, we can also, of course, look for this package, which is this ARI 2D nav gazebo. let me come here. Gazebo, which we have it in ARI simulation, all right? ARI simulation. ARI 2D nav gazebo, launch, and ARI navigation. Okay? This is the launch file, as you can see in the rosject, the launch file that we are running, ARI navigation.launch. Then inside here we are doing several things. As you can see, it's a huge launch file. But basically, besides all the arguments that we are loading here, we are running gazebo here, which is the simulation, the launch file that we have been using till now. We are loading the simulation, and here we have the navigation launch, which in this case I have it commented. So we can, let me uncomment it here. Okay, so some things, do you have this commented, this section of the launch file? Can you confirm it here in the chat? Because I think in the last save, some things may have been lost in the last save of the project. Okay, I'm going to comment this. I'm going to relaunch it again. Without this navigation launch here section commented. All right, so let me rerun it one more time here. So can you tell me, guys, if you particularly have in this ARI navigation.launch file, you had this section commented or not? Or do you have it like this? Okay, well, in any case, here we are launching again the simulation. And this is going to automatically open also RVs, okay, which we are going to be able to access, to see from the graphical tools window. So here, as you can see, it has loaded the map of the simulation, and it has automatically localized the ARI robot here. As you can see in this case, the automatic localization, the initial localization is wrong, because the robot in the simulation is not really here, right? Actually, he is here. It's in this bigger room, somewhere around here, down here, right? It's not here, because here in the simulation is around here. So it's not really here, but it's here. Then the initial localization is wrong. So what we should do is to relocalize it to its real position in the simulation, which is somewhere around here, all right? Then we have to wait here. We have to wait here until everything is initialized. Yeah, let me see. So it's not updating the cost maps for some reason here. Okay. Okay, let me stop this and relaunch it. Yeah, this Ahmed is passing this map passed to lookup transform. Target frame does not exist. Yeah, this error is normal. It happens at the beginning until it receives the transforms. Okay, so don't worry. That error is normal. If you are getting this error, don't worry, because it's expected. It's going to show this error until it receives the transform. So let me rerun it and let's see, because I was getting a different output. Yeah, see? So I am receiving also here the message, as you can see, but this is going to appear, okay, here we have the simulation and RVs. So this message is going to appear until the transform is received, which it takes some seconds because of all the delays here in the simulation. But after some seconds, this error should be gone, and then the cost maps are going to appear here upon the map, upon the static map. Let's see. Let's wait a few seconds and see if this happens. And I get the cost maps loaded. Okay, it's looking like it's getting stuck here. Yeah, this is some, this error has to do with the timeouts, but I don't know if it's going super slow or if it's absolutely stuck here, which it looks like, because it's not loading the cost maps. So basically this should be loading the cost maps here, as you can see, in these light blue colors, but it's not loading them for some reason. Okay, well, something wrong with this demo. Okay, well, yeah, I'm going to look at it now because we have to, unfortunately, we have to finish now the live class. So I will look to this, why it's not working now, this. Then basically what is going to happen here is that the robot gets initialized in a wrong position, as we were seeing, and then we have to localize it here in the correct position corresponding to the simulation. Yeah, so you have to see the position in the simulation and then localize it here. Then once it is properly localized, we can send a goal using the 2D nav tool to the robot, and we are going to see how the robot automatically starts moving towards that direction, okay? Unfortunately, this last demo, I couldn't reproduce it properly here, now in the live class, but I'm going to check now after the live class what happens, and I'm going to update it, okay? So that you are going to be able to run it later without any issue. All right? So yeah, we are going to leave it here for this live class. I hope you have liked it, you have enjoyed the other demos, the perception, demonstration, also the running predefined motions, and you have enjoyed in general the live class. You have learned and taken something from this hour. So yeah, thank you very much for being in this live class with me. I'm going to see you next Tuesday. This week we had to change the date from Tuesday to Wednesday because here in Spain we had some regional holidays. But starting from next week we are going to go back to Tuesday, which is the regular time. Tuesday 18 CEST time, okay? The same time as always. So yeah, thank you very much for being here with me in this live class, and I will see you next Tuesday. Until then, keep pushing your ROS learning. Bye bye.